Okay, welcome to Mr. Burley Teaches, a series of lectures for the AP Environmental Science classroom. Today's topic is an introduction to the atmosphere. Alright, this will be part 1, structure and composition. So we start here, floating above the Earth, and we look down and realize that most of the atmosphere of Earth is hugged close to Earth. Alright, way down there you see the tops of the clouds, alright, and a thin band of atmospheric gases that surround our planet. The atmosphere being a series of gases held to Earth by Earth's gravity, where we are floating, even though outside the space shuttle, we are technically still in Earth's atmosphere. Alright, there is still a hydrogen atom held to Earth by Earth's gravity, and so therefore we are technically still in Earth's atmosphere, although very thin. Alright, a lot of us consider this space. But technically the moon would then therefore be within Earth's atmosphere. So it's really, we don't really know where the atmosphere ends. But what you want to know is most of the Earth's atmosphere is close to Earth, close to Earth's surface. So I gave you an assignment for homework. Alright, this is going to be part A of your assignment, and let's just go over this quickly together. What we're looking at here is atmospheric density. Okay, the density of the atmosphere, the actual amount of atmosphere. Okay, the amount of gases. So when we're talking about the density of the atmosphere, there really are no units. So in your assignment, they had you look at the atmosphere and call the entire atmosphere 1,000. Alright, let's just give it that number. It's an arbitrary number, it has no units. Let's just call the entire atmosphere the number 1,000. So along the x-axis at 0, okay, 10, 20, 30. Okay, at 0 altitude, so at sea level, you look at how much atmosphere is above you. It's the entire atmosphere, okay, 1,000. So when you plotted your points, alright, your graph should look something along this line, okay, and what you see is that with altitude, so as you go up, the amount of atmosphere goes down, and that should make sense. Okay, so if you climb the top of a mountain, there is actually less atmosphere at the top of the mountain than there is at sea level, which is one of the reasons why it's harder to breathe on the top of the mountain. At Mile High Stadium in Denver, they have oxygen tanks for the players. Alright, so there's literally less atmosphere at the top of the mountain. So if you continue to go up and up and up, at some point the atmosphere thins out so much. And again, we really don't know where the atmosphere ends. It just gets so thin. And as long as there's one hydrogen atom held to Earth by Earth's gravity, you're still technically in Earth's atmosphere. This is a pretty simple chart, just kind of designed to show you most of the atmosphere is hugged close to Earth. And they asked you to plot a point. Where would you be, at what altitude would you be if you were above half of the atmosphere and half of the atmosphere is below you? I think it was 7 or 8 kilometers. The point being, all you'd have to do is go up 7 or 8 kilometers in altitude and you'd already be above half of the atmosphere. Alright, so just really driving that point home that most of Earth's atmosphere is close to Earth. Is close to Earth's surface. Alright. You'll see me use this little symbol for Earth. Okay, so pretty simple graph. Just gets your feet wet for part B, which is a little bit more intense in dealing with the structure of the atmosphere itself. So let's take a look at part B. And you probably have graphed, if you set up your x-axis properly, your graph should look a little bit like this, a little bit of a zigzag pattern. Alright, and this we're going to title the structure of the atmosphere. Alright, our atmosphere has definite structure. Alright, atmosphere. Okay, and the structure of the atmosphere is not visual. Okay, you cannot go outside and look up and see different layers of our atmosphere. The structure of the atmosphere is actually characterized by what the temperature is doing. As you go up from the Earth's surface, as long as temperature is going down, as long as temperature is decreasing, you're in that first layer, alright, which is very thin band. Alright, you're in that first layer called the troposphere. All right, now the troposphere is where you will spend your entire life. So let's enhance our note a little bit by putting a little person there, and if you want, you can draw a little hat on him. All right, you will spend your entire life in the troposphere, unless you become a jet pilot or you go up into space, which I encourage you to do. Nevertheless, we spend most of our entire lives in the atmosphere. Even if you climb the mountain, as you go up the mountain, temperature is decreasing. You're still in the troposphere. Other things of note is that 99.9% of all weather occurs in the troposphere. Okay, all storms, all rain, all tornadoes, all hurricanes, all of that occurs in the troposphere. All right, the highest clouds you could possibly see are still in the troposphere. All right, we also take advantage of the boundary between the troposphere and the next layer. That boundary, called the tropopause, is also where jet planes fly. All right, that's where the jet stream is. So planes take advantage of this high upper level wind, and when they're flying with the jet stream, they can save fuel. And when they're flying against the jet stream, it's a bit turbulent and it takes a little bit more fuel, but that's where the jet stream is located. So even if you're an upper level jet plane or a commercial airliner, you're still in the troposphere. All right, and that's going to come into play. It's going to be important later because these jet and plane emissions, all right, now we're emitting atmospheric gases way up here in the troposphere, at the top of the troposphere. Okay, every volcanic explosion, I'll draw a little volcano here, every little volcanic explosion, the ash, dirt, and debris is in the troposphere. Sometimes it can get up into the next layer. As you go up, temperature decreases. Okay, and then at some point in the atmosphere, the temperature will kind of pause. All right, and they call that the boundary. That's the tropopause. All right, and then the temperature will begin to increase. All right, so something is in this next layer called the stratosphere. Something is in this layer that causes the temperature to increase. All right, something is heating up. And by this chart here, you can see what is in this layer. It's the ozone layer. All right, in the stratosphere is where the ozone layer is located, all right, represented by these little O3 molecules here. And the ozone layer actually absorbs heat energy from the sun. Okay, so if we draw a little sun here, on a daily basis, UV energy comes into Earth's atmosphere. All right, and luckily for us and for most of the life on Earth, that UV radiation is absorbed by the O3 molecule, by ozone. There's different types of UV radiation. There's UVA, UVB, and UVC. UVA is the common cause of wrinkles, UVB is the common cause of sunburn and skin cancer, and UVC doesn't reach Earth. If it did, we wouldn't be here, or life would look very, very different, because it is high energy radiation. UVB is high energy radiation, enough to cause skin cancer. Okay, it burns you, it burns your skin, sunburn. All right, but going back, because that energy is absorbed by the ozone, this layer, the stratosphere, is actually going to heat up. All right, so that's why we have that temperature inversion. All right, there's a source of heat in that layer. Back in the troposphere, the source of heat is the Earth itself. Okay, as sunlight comes in, the Earth warms, and then as you move away from that surface, temperature is going to go down. All right, it's kind of like putting your hand on a hot stove. As you move your hand away from the stove, it's going to naturally get cooler. You're getting away from the source of heat. The Earth is the source of heat in the troposphere. In the stratosphere, that absorption of UV radiation is a source of heat, so temperature rises. Okay, now, things get different in the stratosphere. It's a very dry place. There's not too many air molecules. Remember, most of the Earth's atmospheric gases are held close to Earth. All right, so in the troposphere, if you get to the top, you're already above most of the gases of the atmosphere. So the ozone, there's not too many gases up there. So in the stratosphere, we're already of what you and I would think of as being space. All right, in the stratosphere, you could see the curvature of the Earth. There isn't too many molecules up there at all. All right, so as you continue to go up in the stratosphere, temperature is again going to pause. You're at that boundary to the next layer. We call that the stratopause. Temperature pauses. And then the next layer is characterized by temperature that is again decreasing. Alright, so you know you're in the next layer, the mesosphere. Meso meaning middle. You're in the mesosphere if, with altitude, temperature is decreasing. Not much is going on up here. You're moving away from the source of heat, which is why temperature is decreasing. What is the source of heat that you're moving away from? If you guessed ozone, you were right. As ozone is absorbed, temperature is going up, but at some point you're going to be moving away from that source of heat and temperature will decrease. That's the mesosphere. Alright. The only thing that's really going on up there is if you see a shooting star at night, you're seeing a piece of space rock, space dirt and debris burning up in the atmosphere, high in the atmosphere in the mesosphere. Okay? There's so few molecules up here. As Earth passes through space, dirt and debris begin to interact with those molecules, heat up, and burn up. Alright, so luckily, the mesosphere is at these altitudes. Think about if the mesosphere and meteors burning up at lower levels. If meteors burned up at lower levels, there might be more opportunity to hit Earth, cause mass extinctions. Alright, so luckily our atmosphere is structured in this way that meteors are burning up here and not closer to Earth's surface. Alright, or we might not be here. Biological evolutionary clock might be reset too many times, not allowing life to evolve. Alright, so there's a lot of really great things about Earth, and the atmospheric structure is one of them. Okay, so continuing right along here, at some point in the upper atmosphere, temperature will again pause. Alright, we're at the mesopause, and then begin to increase in the thermosphere. Thermo, heat. A couple things about the thermosphere. There are so few molecules in the thermosphere that temperature up here isn't what you would think temperature is. Alright, when you and I think about temperature, we think of air temperature. But there's no air up here. There's only very few molecules. So this temperature line doesn't really necessarily mean air temperature. Up here in the thermosphere, it's talking about kinetic energy. So even though there's one hydrogen molecule floating up here, so it's technically our atmosphere, that hydrogen molecule, it's cruising, it's flying. All right, so interaction with the sun's solar particles coming in causes these molecules to shoot. All right, so we say that the temperature is going up. In this case, we're talking about molecular motion. Alright, you can see the other things that are going on up here. The Aurora Borealis. If any of you have ever seen the Northern Lights, I aspire you to do so. You're seeing interaction with solar particles in the upper reaches of the atmosphere. The only other thing that's going on up here is this is my International Space Station and satellite technologies. The shuttle, when it was operating, the Hubble Space Telescope, they all orbit our planet in the thermosphere. Okay, so we're talking basically, we're basically in space. Alright, that's a pretty heavy-duty note. Okay, the structure of the atmosphere. There's 4 layers: troposphere, stratosphere, mesosphere, thermosphere. All characterized by what the temperature is doing. Alright, that's how you know you've crossed into a different layer. And then also in those 4 layers, there's some other things going on. Okay, the troposphere is a very special place. All weather. We are there, air traffic. Okay. In the stratosphere you have the ozone layer. In the mesosphere is where meteors are burning up. And in the thermosphere, at the edge of space, you have our satellites and our International Space Station and the Aurora Borealis. Okay, so hopefully that makes sense to you. That's a heavy-duty note. This course will deal mostly with what's going on in the troposphere. We will deal a bit with the ozone, alright, which is in the stratosphere. But for all intents and purposes, most of this course in pollution and air quality will all take place down in the troposphere. But it's important to realize the structure and gather an appreciation for the beauty and the perfection of Earth's atmosphere. If you have any questions, please bring them to class. I hope that you got these notes so you can answer any questions. Okay, here's just another image. Alright, you can pause the video if you want and take a look at that one. Alright, so let's move on to atmospheric composition, the chemistry of the atmosphere. Okay, composition, what it's made of. Okay, the actual gases. And the gases of the atmosphere can be broken up into two kinds of gases. All right, there's permanent, what we call permanent gases, and then there's variable gases. Okay, start with permanent gases. Those gases whose concentrations do not change are permanent gases. All right, do not change. So, for example, nitrogen is a permanent gas. Our atmosphere is about 78% nitrogen. All right, you can open up all the nitrogen valves you want on planet Earth, and you'll never dent that number. The concentration of nitrogen does not change. All right, oxygen is a second permanent gas. About 21% of our atmosphere is oxygen. All right, you should know that oxygen is reactive. All right, causes rust. All right, and it cycles through the atmosphere as does nitrogen. It's also nitrogen cycle. And argon is about 0.9% of our atmosphere. Those are the three permanent gases. Those concentrations do not change. One point I will make is over geologic time, those concentrations do change. If you're thinking about your geologic timeline, the amount of oxygen fluctuated on Earth, causes and effects of that. However, for all intents and purposes, let's consider nitrogen, oxygen, and argon permanent gases. All the others are variable gases. The concentrations do change. And those are the ones, all right, if you did your math, all those others are only 0.1% of our atmosphere. But these are the ones that we do have to consider. And this is where our issue of global warming is going to come into hand, because greenhouse gases are variable gases, okay, as is ozone. All right, those concentrations do change. So let's take a look here on the next slide. Okay, here's what we're talking about. All right, nitrogen, oxygen, and argon. All right, if you look here, that is 99% of our atmosphere, permanent gases. All right, and then you have the variable gases. All right, and the important ones here are carbon dioxide, CO2. All right, it is a greenhouse gas, meaning it traps energy to Earth's surface. All right, it's going to heat the planet. And here is the amount of carbon dioxide in our atmosphere. It's actually about 0.038%. All right, 0.038%. Not too much. All right, but we are having an impact on that. All right, to continue reliance on fossil fuels and coal-fired power plants, okay, all are contributing to the amount of greenhouse gases going into our atmosphere. We're going to talk a lot about that. All right, another one is methane, okay, CH4. All right, methane is also a greenhouse gas. All right, trace amounts of it in the atmosphere. Just trace amounts. But what's important to know is it is 23 times stronger of a greenhouse gas than carbon dioxide. It's so much more of a heat trapper to Earth. All right, so where is the methane? How much methane is in our atmosphere? Is that number going up? And you'll see that that's one that we're going to end up being concerned about. All right, and then a third variable gas of our concern is ozone. Okay, the O3 molecule. Very small traces of it in our atmosphere, but it is so important to life. All right, it blocks UV radiation, which would otherwise fry or zap bacterial life, really leading to a different place. All right, and humans were doing something, right, that was contributing to the destruction of the ozone layer. Okay, we were adding ozone-depleting chemicals to the atmosphere and deteriorating that ozone layer in the stratosphere. So those are three variable gases whose numbers can change and are going to have an impact. There's going to be a cause and effect relationship. With the composition of the atmosphere, there's a lot of variable gases, but those are three that we're going to be concerned with. Okay, and I think that's a nice way to present the composition of the atmosphere in permanent and variable gases. If you have any questions, please bring them into class, and I'll continue to move on here. Alright, so at this time I'm going to end this lecture. Alright, the next lecture will be about ozone. We're going to take a closer look at those three important variable gases. Alright, but that is a nice way to look at the structure and composition of the atmosphere and introduce ozone as a variable gas, one that humans contributed to depleting the ozone layer. Alright, so I'll leave you with this little cartoon. Alright, our atmosphere is very balanced. Okay, we're going to get into that. But please gain an appreciation for the structure of our atmosphere and what makes it up. Alright, that'll conclude this lecture. I'll see you next time when we talk about ozone.